in the CER, the claim evidence reasoning, your claim is like the old school hypothesis. Anybody familiar with the scientific method out there? Heard of it, done it before in other classes? Even if you haven't heard of it per se, you've been doing it in your bio and chem classes. But is anyone aware of this?
I've definitely heard of it. I just don't know offhand.
Yeah. Okay. So that's basically the nuts and bolts behind any type of scientific experiment. You make a claim, you want to test it, keep on testing it until you can verify your claim. Then after the evidence is verifying your claim, then you want to make a conclusion, the reasoning part. All right, based on my evidence, based on my testing results, based on my data charts, based on my graphs, based on the equations of these graphs, I can clearly state that the acceleration due to gravity, for example, is 9.81 meters per second squared, because my data proves it. And you're saying all this stuff in your reasoning section, right? Reasoning is your conclusion. Everybody cool on that so far? I'll move that out of the way. So claim is hypothesis, evidence, testing, your data, etc., right? And reasoning is your conclusion. Now, I'm going to now write up a couple of scenarios for you. And I want you to tell me. I will just pick on somebody, pick on you. I want that person to tell me which one of these situations is an example of constant velocity. So my claim is, well, I want to answer this. The answer to this question is going to be my claim. Which car below is an example of the CVPM? Remember that old packet we did a couple of weeks ago? You should still have that in your possession. Again, with the test tomorrow, you can use anything you want. You have your CVPM, you have your book, you have your notes. I can't restrict you from that. What am I gonna do? Reach out like the girl from The Ring and take your stuff away? Bad reference. Okay. All right. So which car is an example of the CVPM? I'm not saying that I can do that per se, but you don't want to find out. All right. The first situation, a car in cruise control moves at a constant 25 meters per second east. I think this is going to be rather easy, I hope. So now claim number 2, a car changes speed from 0 meters per second to 10 meters per second going east. Sophia, I hope Lorenzo, I hope your mic works. Could you tell me which one of these is an example of constant velocity? Or tell me in the chat if your mic is still not working. Cameron, could you tell me which one is an example of constant velocity? Situation 1 or 2?
You said me?
Cameron, yes. of these two, which is a constant velocity?
One.
Yes, it's dead giveaway. I was cruise control, constant.
Yeah, I did read it.
Yeah, just read things first. That's going to be important. Make your claim. So yeah, situation one is the cruise control, or example of CVPM is the cruise control example. So what we're going to do next is, like I would send you to a breakout or send you to a lab group right now, and I would say, what are you going to do about it? How can you prove to me that that is a situation with constant speed? So we have a claim, situation one or number one, whatever. Situation, I can't spell, huh? Situation one is an example of constant velocity, the CVPM, an example of that model. So one experiment can do, okay, right? We need to come up with an idea, an experiment. So evidence is a couple of parts. What kind of experiment you can do, right, to verifies the claim. And as we saw in the little short video, we could have two students, right? And you can use this when we go to breakouts. You can totally use this and for the different scenarios that I have, because I'm going to say that the thing that we do today is part one of your exam for tomorrow. So please be paying attention here. Please be writing these things down. You're going to upload these notes. I want the notes uploaded by 12:30. Nothing later than that. Okay, I'm not going to chase you guys down. I don't want to hear any other excuses that whatever it is, it's irrelevant now. I get things in on time. So evidence. What kind of experiment verifies the claim? Well, one experiment, I could have, two students in the experiment, right? Oops, one student is a timer. One is, I guess, the experimenter, the guy with the car, right? So as the car rolls, each let's see. So as the car rolls, the timer yells the seconds, yells the time, yells out, every second that the car rolls, the timer yells out every second, right? So if he yells out 1 second, yeah, trying to come up with different ways. So as the car rolls, the car at equal time intervals, yes, So as the timer yells out 1 second, then the second student places a marker down for each second that the first guy yells. So again, trying to make this easier. So as the car rolls, the first student yells out each second, right? And then the second student is going to place a marker down every second that the first guy yells out. So the first guy yells out 1, second guy puts down a marker. 2, put down another marker. 3, and we're going to go all the way to 5 seconds. Let's, use that time interval, right? From 0 to 5 seconds. So that's one experiment that we can do there. So from that experiment, where now we have a marker down for every second, we can start to build a data chart where we have the marker is going to mark the position that the car has that the car has passed for every second that the timer student has yelled out. So we can build up a data chart that looks like something like we've seen before. So we can have a position clocked for every time. And if we want to verify our claim that the first situation where a car is moving at 25 meters per second is a situation of constant velocity, then our data chart will look something like this. So we have, let's say we start off at 0. In the first second, let's say that this car is moving pretty good. We have moved 25 meters in the first second. So the guy with the timer is yelling out 1. I say that this car is moving pretty fast, and he puts a marker down at 25 meters. And then 1 second later, he yells out 2. Then we see around 50-ish. Because in reality, it's not going to be, a lot of times it's not going to be just exactly equally spaced. It might be 24.8 or 51.5 or something, but it's going to be relatively equal. And then he yells out 3. And we have something like this: 75, 4, 100, and 5, 125. So now we have a 5-second run of the cart, and then we've tracked these positions for every second. So we've seen this before. We went from 0, 5, 10, our nice little example from before. But let's say we go 25 meters per second. So the car would roughly travel 25 meters every second. It might be 24.7, roughly 25. So we're just going to do exactly 25 meter gaps for every second, just to keep things simple. So our experiment is to do just like we did in the video. Place a marker down for every time the guy yells. He says 1, you put a marker down. 2, marker down, right? And we start collecting the information, collecting the data here that we normally collect it in a data chart. So now if we go from the data chart to what's our generally, what's our next step from data chart to what?
Position time graph.
Yeah, we can do a position time graph. That's what we've been doing so far. We know that this is going to be the y-axis, it's going to be the x-axis. All right, so we can go to graph. Let's graph our data. So what we're doing here is we're interpreting the information. We are gaining evidence. We made a claim, now we're making evidence. So our graph is here. Okay. Time in seconds. Position in meters. So we can go 5. And then every second we go 25 meters. Okay, getting bunched up here, but you get the idea. So you can plot your points if you wish, or just draw the best fit line. If you have graph paper there, of course, that'd be nicer, but you don't need graph paper. And this being 0, 0. So again, this is a pretty nice linear relationship, but you're not always going to get that. So if the points are off the line, you just want to draw a best fit line through all those points, no matter what. Okay, it doesn't have to connect all the dots. You don't want to do a connect the dot scenario. So some of these points I didn't draw them accurately. It doesn't matter, because a best fit line is just that. Whatever the data points are, if your data is telling you that this is linear, and it is because the gaps are the same for every second, then you just worry about drawing a best fit line. Don't worry about connecting the dots, because generally speaking, you won't be connecting the dots. So now we have a data chart. We've gone from data chart to graph. We can make an equation from this, which is something that I'd like you to do as well. So our equation is going to be a version of the slope form equation of a line. So y equals mx plus b, that's from your algebra, but in the y-axis here, remember this is y like in your math classes, but in physics, this is a real quantity. This is going to be your position, x. Our slope is what? Who can tell me what the slope of a position time graph is? Definition that we've had for a while.
Isn't it the x value?
No, the slope is something else.
Velocity.
Yeah,
Rise
the
over
slope.
run.
Right. Well, that's the definition of slope. But I want the physical quantity of a slope is the velocity. So this is slope here, and you're back in your math days, but in physics, for here, it's going to be my velocity. And then the x-axis, the variable on the x-axis is time. There is no y-intercept, as we can see here. So this would be our nice equation of this line in terms of physics, physical quantities. So we have data chart, we have graph, we have best fit line, we have an equation of the graph. We can even do a motion diagram. Right, so, and in the claim, or the claim that we chose, the car is going 25 meters per second to the east. So not only do these values in the y-axis here for position, not only be positive, but this is the direction of going to the east. So positive values are east. If there were negative values down here, that would be the westerly direction. Notice that there is no negative time. Time can only be positive times a scalar. So you have nothing, you won't ever have anything in this domain. So our motion diagram will look something like this. So we say 0, and every second we're going 25 meters. So you want to set up a motion diagram. And the reason why you want to do all this stuff, because you want to tell the viewer, you want to give the viewer as much evidence as possible to convince them that your claim is correct. Your claim that situation 1 is a constant speed. Well, my data chart shows me that it's linear, equal time gaps. My graph shows the same thing as well. My equation is going to describe where that car is going to be at any moment in time. My motion diagram also tells me that. So every second, I'm going to start at 0, and I'm going to put a dot for each position at every second. So every time the guy yelled out a second, we have placed a marker at equal position gaps. So second number 1, we draw a nice little circle. That's where the car is at 25 meters. Another 25 meters in second number 2, he's at 50 meters. 3, 75, 4, and 5. So it's like thematically linear. This is as linear as you can get for this experiment. And we know that the data is linear because the gaps are equal for every second. So this will be my motion diagram that describes the data chart, the graph, and the equation. All right, so now that you've done all that, you can then provide your conclusion or your reasoning. And you don't have to stop there with your evidence. You can do something more if you wish, but your reasoning is like the conclusion of like your lab report, conclusion or evaluation. Okay, CER. All right, so based on, something like this, based on the evidence, and you don't have to write this exactly for your test or your homework assignment, but this is just an example, a baseline. So based on the evidence from my data chart, graph, equation, the line, and hereby okay.
Never mind, he's back. Hi, Mr. Kelly.
Hey, what's up?
Hello.
Hi. All right, so sorry about that. All right. Let's see. Okay, one moment. Okay, so let me get back to my screen here. So internet issues, it always kicks me out here. All right. So did we get to this point here? Okay, so where we left off, we have the reasoning part of the CER, where we were answering the question based on the evidence from my data chart, graph, evaluation of the line, my motion diagram. I hereby verify that the car in number 1 moves at a constant velocity. There are equal position gaps for every second of travel. The data is linear. You could, just bring all that stuff that you've learned into your conclusion statement. So We then went on to the breakout session where we had a sample claim evidence reasoning CER, where we're to make a claim based on this question here. Which car below is an example of CVPM? A car travels at -5 meters per second. A car travels 20 meters per second east. And 3, a car goes from 17 meters per second to 0 meters per second in 3 seconds west. So which car or cars is an example of CVPM? Let's go with Cameron.
The second one?
Okay, are you sure?
Not really.
Tell me what you're not sure about.
Which one I'm choosing?
Okay. Do you know what constant velocity is?
Kind of.
Tell me what you think it is.
Something that's moving at like a constant speed and direction.
Okay. Now, based on that definition, let's look at number 1. Is this speed constant, or is there a change? Meaning, does the number change?
No.
Therefore, it is what?
Not an example of CVPM.
If the number does not change, what if anything doesn't change in life, whatever it is, what is that an example of? Is it constant? All right. So in number 1, is the number staying the same?
Yeah.
Therefore, number 1 is
constant velocity.
there you go. What about 2?
Yeah.
You sure?
No. Actually, no, I don't think so.
Okay. 2 is an example of CVPM as well, because the number doesn't change. Number 3 is not an example of CVPM because we're going from one number to another number. The thing that you want to keep in mind, Cameron, and anyone else that may have this question, I'm sure there are several. If the number doesn't change, it's constant. You know, like English vocabulary word, right? It doesn't change, so therefore it's going to be constant velocity. So candidates 1 and 2 are examples of CVPM. Okay, let's go with Leah. What experiment, like just using number 1, what experiment did you use to get evidence that number 1 is a constant velocity? Did you do that part? Anyone want to help out? Did anybody get to that part where we devised an experiment?
I did an experiment. It's basically just the same thing as the one you gave. I said,
go ahead.
You could have 2 students, one of them being a timer and the other one does the experiment. One could have a model car, and as it moves, the timer would yell out time intervals, and the other student would place down a marker down for each interval. And you repeat this situation. You would repeat this experiment for each situation, except for this other situation, the car would be going in the other direction.
Okay, so so -5 meters per second. Let's go with another student. Let's go with Diego. 5 meters per second, -5 meters per second is what direction, east or west?
West.
That is correct. It's going west, and then I gave you the direction for question 2 is going east. So yeah, we're basically doing the same thing as we did in the example. So Monte, what did you do with your data? What kind of data do you have? I can write it down for us.
I made a motion diagram.
Okay, before we get to the motion diagram though, did you do a data chart?
No.
That's part of the example. I want you to do everything that I did in the example. All right. So don't just pick and choose or and all that. I want you to do the entire thing. So anybody give me a data chart
For which situation?
or the -5. -5.
Well, for second 0, it's 0 because it hasn't moved yet. And in the first second, it's -5.
Okay, do we
And for the second, for the second, it's -10. Then it goes on with -5. So it'll be -5, -10, -15, -20.
okay, so -5 here and what's here?
1.
Okay. And then -10 and 2
2.
and so on, all the way to 5. Okay.
Yes.
So if you guys didn't do this, this is an example that you can do. You don't have to do it in this order, but just as long as your gaps are the same for every second,
Mr. Kelly,
5-meter gaps for every second, then you're okay. Yes.
Mr. Kelly, can you go up a little? Can you go up more? Okay.
I would advise you guys not to, get into the habit of taking pictures. You should try to stay with it. And if you miss anything, this video will be on my YouTube channel. All right, just in case I went a little fast and you didn't catch me in time, go back and view the video again at my YouTube channel. Speaking of which, I'll put that down here in a second. All right, so -15, -20, -25, and 5. Okay, great. So we got that going. And we do likewise with the second situation in question 2, where the car is going 20 meters per second to the east. We have the same situation here, where we're going to have gaps of 20 meters every second. In this case, it's 5 meters every second, but to the west. These negative signs indicate that it's going to the west. So let's do a graph and illustrate that. Exactly, okay? So the positive y-axis here that measures positions with the symbol X, this is going to be going towards the east. So the positive domain is to the east, negative domain is to the west. So this is going to be -5, -10, -15, and so forth. So we have 1, 2, 3, 4, 5. So every time that the car rolls along and the student yells out a time, if he yells out a second, yells out each second, then he's going to place a marker down. In this situation, the markers happen at 5-meter gaps going to the left or going to the west. So this is the west domain. This is east up top. This is west down here. So this is 1, 2, 3, 4, 5. And then we have -5 and 1 placed here. 2 and -10, 3 and -15. Monte, are you following this?
Yes.
Okay, I want you to write this down. This is question number 1 of your exam. I want you to do well. I want all of you to do well, especially those who are these. All right, so I want this to be an easy time for you. All right, so -5, 1, 2, -10, 3, -15, 20, -4, and -25, 5. So we're gonna have a situation that looks something like this. Who cares if it's crude? What kind of line are we drawing? A blank line.
A linear line.
2 words. Starts with a B.
Best fit.
Best fit line. Okay, these points. We're not gonna draw a line that connects the dots. I'll do the equivalent of throwing your paper in the trash. Don't do that. Do a best fit. Even if all the points are off, just draw a line, a straight line that best fits your data. In this case, the lines are all off axis. Who cares? That's going to happen most of the time. But we want a line of best fit because we want to take the slope of this line. The data points are the data points. It's how we scaled it. It's how we drew it. Doesn't matter. We're good. And then we make an equation. So in this case, what could be our equation? Let's see. Tigran S. You come up with an equation?
No, I didn't get to that part yet. I just did this part.
You just did this part, okay.
Yeah.
A little bit of time, all right. So let's just go ahead and fill in the gaps as a time that's remaining. So we have a negative slope. This is a negative slope, and if you go back to your notes, we know that the slope of position time graphs are velocities. So this would be, we could say, we know velocity equation is delta x over delta t. The slope is the velocity. All right, so then in making this equation, we can say x is equal to negative v times t. Why negative v? Because the velocity is going towards the west. This is a negative slope. Okay, this right here will give us our negative slope. But before we had x equals vt because the velocity was a positive slope. Now negative vt because the velocity is negative. All right, and then motion diagram.
Wait, Mr. Kelly, that's all you have to put for the equation?
Yeah, an equation.
Because for me, I plugged in -5 for the velocity.
Yeah, you can do that. That's
Oh,
fine.
okay.
Yeah, you can say x equals negative vt or x equals negative 5t. So yeah.
Okay, thank you.
Either one, guys, you're good because Lala knows that that is the slope. You all should see that that is your slope. You don't have to do this. You have the choice, x equals negative vt or x equals negative 5t, where negative 5 is the velocity, the slope of this line. So Monte, your motion diagram, tell us real quick. How'd you set it up? Tell me so I can write it.
I went from right to the left.
Okay, describe that for me because I want to draw it.
Every second I moved down by 5 meters.
What are your numbers? What are your numbers on your line? You went from right to left. Okay. So if this is 0 and these are negative, correct? Is that what you're telling me?
Yeah.
All right, what are my numbers on this line?
-5, -10, -15.
Thank you.
-20, -25.
All right, cool. Thank you. Okay, so I'll just leave it at -20. So what would my arrow look like? What's my?
To the left.
Okay, so I draw this, and what happens at 5?
You put a dot.
Okay, good. Thank you. All right. Good job. All right. So yeah, I mean, everybody should have something like this, and it goes to -25 and so on. So we just basically reverse direction. So that would be our motion diagram for this. And then I won't write up the reasoning, but this is question number 1. Hold on to this. Now, the notes are what we did before this example. Okay, so by 12:30, I want you guys to turn in everything before I started writing breakout sessions. So these first 2 slides, I need to see those. Okay, so that's going to do it. And then your test tomorrow, hold on to question number 1, which we just did, and you're going to have like 2 or 3 extra questions tomorrow.
Can you go all the way to the top for me, please?
At the top of this?
All the way to the top whenever we first started the writing.
No, I cannot do that because
Okay.
class is over. All right, you have to stay with it. You have to stop me while I'm writing, all that. So, okay, I'll see you guys tomorrow. You have any extra questions? I'll post the video up on the YouTube. Let me tell you my YouTube channel.